This video explains the example of designing reinforced concrete columns. It has a cross section 450 by 450. The fitments that is given in the example is R250 and 10 fitments. Now we need to know the reinforcement required for particular design load and design moments. Now concrete compressive strength is given in the example 25 megapascals. Yield strength of the reinforcement, the longitudinal reinforcement that are shown here is 500 megapascals. Permanent dead load is given G 1832 kilonewtons. Dead load live load imposed action is given Q is equal to 815 kilonewtons on these columns. And also the design axial load 3618 kilonewton is given here, and moment at two end, one end is 0 kilonewton meters and another end is 86 kilonewton meters. That is the ground floor column. So we are designing these columns. It has footing here, the ground floor, the dimension is given 4.8 meters. There is a beam here, and that is the level 1 continued that columns. Now our interest is to find this reinforcement, how much reinforcement we should provide that into these columns. So let's say first of all we need to check whether the column is short or slender. So for that we need to have a ratio L over our R. Before that, I think I just like to read that clause called 10.1.3 about the brace columns. So column in a structure for which the lateral action applied at the end in the direction under the consideration are resisted by the component such as masonry, infill walls and shear walls. So we are designing these columns as a brace columns here. So we designing according to the clause 10.1.3.1. So it's the brace columns. Now we need to calculate this called slenderness ratio, L over R, effective length over radius of gyration. Clause 10.5.3 is to calculate the effective length. So we're going to calculate effective length and we're going to calculate radius of gyration. We're going to take the ratio, that is the slenderness ratio of your columns. So clause 10.5.3, couple of page from the standards on that down here, clause 10.5.3, it is the effective length of the columns. So its effective length of the column shall be taken as K times LU. So that's I written here, clause 10.5.3. Once you have that K times effective length is K LU, K 0.85. Now there is a procedures as well. If you go to the clause 10.5.4 in the last examples, you can find the end rust strain coefficients. You can find end rust strain coefficients here, and this is unbraced frame. For braced frame, you can calculate these end rust strains at one end and another end, and you can find the K value. That is a quite long process. But the problem here that we don't know the footing, how the footing will have a rust strain provided onto these columns. It's very uncertain about the rust strain provided by the footing, that end rust strain that you need to calculate gamma 1 and gamma 2, because gamma 1, let's say here, gamma 2 is here. We can calculate gamma 2 here, but gamma 1 is a little bit challenging here because of the footing that is very uncertain. So in that case, we just take a conservative assumptions, K equal to 0.85. So effective length is equal to K, which is we just assume 0.85. LU is the clear height. Clear height meaning that if you are just taking this 4450, that is the clear height that we are taking it here, 4450, equal to 3783 millimeters. Now I just mentioned about this footing uncertain. Now if you go to the clause 10.5.2, because we just calculated the effective length, we calculated effective length. Now we need to calculate the radius of gyrations, that is the R. Now that radius of gyration definition is given in the clause 10.5.2. What is the definitions? Radius of gyration shall be calculated for the gross concrete cross section. For a rectangular cross sections, yes, it is a square is a rectangular cross sections. For rectangular cross section, R shall be taken as 0.3 D. So 0.3 times D is 450, equal to 135 millimeters. So in that case, slenderness ratio is equal to LE over R is equal to effective length we just calculated 37183, radius of gyration 135. So slenderness ratio is 28. That's the first steps that we should calculate to check whether it's a short columns or slender columns. Now close 10.3.1a, just some page across, close 10.3.1a, that is for the brace columns. It says that if you have a effective length less than or 25, it is short columns. If it is greater than 25, is a slender columns, and it should be taken one of these largest. So I have written here the limit of L over R ratio would be maximum of 25 over alpha C 38, FC dash 28, 1 plus M1 star over M2 star. Now there is a note here that if you have M2 star is less than or equal to this value, then your ratio M1 over M2 star would be taken -1. So let's check it out. M2 star is greater than or 0.05 D N star. Let's check whether this condition is valid or not. So 0.05 D times N star. So 0.05 D is 450. The depth of the cross section is 450 divided by thousands to convert into the meter. So we are working in the kilonewton meters. So here we have a kilonewton meters. So therefore is in meter, and 3618, that is the N star design force, 3618 kilonewtons that I substitute here. It gives me 81.4 kilonewton meters. And if you check M2 stars, M2 star is given in our example 86 kilonewton meters. So 81.4 is less than 86. It says that if your M2 is less than or equal to basically that is less than here, so is less than or equal to this one. In that case you take M1 over M2 is equal to -1. So that is taken -1. So if I substitute -1, 1 minus this -1 give me 0. 0 times something is 0, so you have 25, 0. So limit would be 25. So the slenderness limit that for the brace columns that we found is 25 here. Now if we have 25, then we can compare against our slenderness ratio that we calculated. We calculated 28. So the slenderness ratio that we calculated was 28, which is greater than 25. It says here if it is less, then it is short columns. That limit is this calculated slenderness ratio is greater than our slenderness limit is 25, then the column is slender. Now in the next video we're going to calculate the moment magnifier. We classify that column is slender, so we're going to design as a slender column, and in the next videos we will proceed on calculating this moment magnifier and buckling loads. Thank you.